Good morning, everybody. I think it's time to get started. My name is Randy Rorden. I work for PTC. I'm a software development director for them. You may have heard of, in the IoT space, one of our subsidiaries is ThingWorx. It's a business group of PTC. I don't work for that group. I work for a different part of the company. We provide a real-time Java solution called PERC, and I am the manager for the R&D for that product. And I'm here to talk to you today about Linux and real-time Java for the Internet of Things. We're going to have a presentation, then a demonstration, hopefully, if it works. And it has been described as an out-of-this-world demonstration. You'll understand when you get to it. And after that, we'll have a Q&A session, so please hold your questions until then. And I want to start actually with a question to you. Who in this room, by show of hands, has used Java in an embedded or IoT project of some sort? Oh, excellent. Very good. And now, the big question of you, how many are considering using Java in a future embedded or IoT-related project? Okay. Not as many. Maybe I can convince you to consider it down the road here. All right, so let's get started. I wanted to begin with a little bit of context, give us some perspective on this whole IoT mega trend that's happening to us right now. And when you talk about the things in the Internet of Things, you're talking about embedded systems, of course. And digital processing has been embedded in things since the earliest days of computing. If you go back far enough, you'll find mainframes and mini computers that were used for SCADA systems controlling oil and gas production and water treatment plants back in the 1950s and 60s. I'm not that far back, but in the 70s and 80s, I was a hardware engineer building embedded systems with 16-bit and 32-bit microprocessors. And early on, we had to design the board ourselves, pull together the CPU, memory, peripheral interfaces, and lots of glue logic to make those parts work together. We built custom design boards. They were very expensive to manufacture and very time-consuming to get out to market. And for software, we used roll-your-own kernels and executives, mostly interrupt handlers for timers and things. UART interfaces and such like that. And a lot of the code was written in assembly. Those were the days. I don't miss them at all. In the 80s, we had the IBM PC come on scene, and semiconductor vendors started building chipsets, pulling a lot of that glue logic into single chips or a set of chips. And they also published reference designs. And a second tier of vendors started appearing, building merchant computer boards, they were called, and for the embedded community specifically. And so you could buy hardware off the shelf using these chipsets and reference designs. And the manufacturers of these boards collaborated to create standards for form factors and bus interfaces like PC 104. And you could buy now the hardware off the shelf. And for software, you could go to a commercial real-time operating system vendor and start using their software instead of rolling your own kernels and executives, getting a little further up the stack that way. So products like Vertex and VxWorks and PSOS, only some of those still persist today, but there are still a few out there, and some of that code is still running on devices tucked away in various places around our planet. Fast forward to today, we've got, thanks to the smartphone revolution, multi-core SoCs with on-chip interfaces, Ethernet interfaces to all the kinds of peripheral devices you could care about, stacked memory and flash and DRAM, and inexpensive MEMS-based sensors, also nicely delivered to us from the smartphone generation. And open source boards are a cool new thing now, right? So we've got Arduinos and BeagleBones and Galileo boards that are open source and accessible to you. Now you can buy a credit card sized computer, fully functional for less than $50 and ship that with embedded Linux and high level languages like C++ and Java. So we've come a long way in those several decades, and it's now commoditized the hardware and software components of embedded systems enough that it's really opening up new opportunities. And I'd kind of like to talk about that, in specific, the Internet of Things. And as most innovations have come about, the Internet of Things is really the result of the convergence of a lot of mostly unrelated technologies, one of them being embedded systems. And all of the commoditization of hardware is allowing us to sprinkle intelligence and storage around the planet like magic dust and everything that you can imagine. Intelligence is the new ingredient in lots of products, from cars to appliances to smart doorbells and things. So it's amazing what you can do with embedded devices now. Cloud computing is another track and another technologies that's contributing to IoT. Specifically virtualization and software-defined networking. Now the infrastructure, the IT infrastructure that you need is commoditized, and you can allocate it and use it on demand and scale it up as you need with no overhead and additional cost. So everybody can focus on what they're creating as the value of their product, which is in the software, and not have to spend a whole lot of time and effort and money working on the silicon and the copper that it takes to run that software. Big data and deep learning are another major advancement that are taking place now. So organizations can glean and understand and gain new insights about their products and how they're being used and the customers that are using them from massive amounts of unstructured data. Artificial intelligence is giving us things like speech recognition systems and computer vision systems and autonomous behavior of remote devices and systems. And of course, connectivity is ubiquitous, and wireless standards are coming along now. A lot of them, unfortunately, they're competing, but the best ones will win out. And we're connecting all of these little devices and bridging the final gaps in the few meters between them so that we can create these massive networks of things for the Internet of Things to take place. So all of these technologies on their own are making incremental improvements and productivity and cost reduction and capabilities of organizations. But together, they've converged to create a whole new thing, a new opportunity that's really greater than the sum of its parts. And that is the opportunity to build smart connected products and deploy them in all new kinds of ways with new business models, such as product as a service, where a company can deploy a product to the field and just charge users when they need it and when they use it. GM is working on a system that's going to let you go rent a car, essentially at a parking space anywhere in a city, and drive it away using your smartphone. So the Internet of Things, you've seen this picture or form of it in probably every presentation this week. It's touching everything in every possible field you can imagine, and it's putting intelligence in devices, as I said, you'd never expect to find it. Anything with some power on it will become an intelligent device. This diagram of a centralized cloud surrounded by a field of interesting things that are communicating with it is a very simplistic view of the architecture of the IoT, and as you can realize, it doesn't scale very well. If you tried to do this with 50 billion devices, you'd quickly run out of all of the bandwidth and then all the networks and all the storage and computing power of all the data centers in the world, and not be able to process it all. So the solution that has been proposed by many to solve that issue is to push some of the intelligence and storage out to the edge. Cisco likes to call that fog computing. You put some intelligence and capability at the edge of the network so that it can filter the data, reduce the amount of it, aggregate it, and save it for when it needs to be transmitted to the cloud. And then it can also do other things for you out at the edge. So the elements that are performing that function are often called service gateways or M2M gateways or IoT gateways. And in this talk, I'll call them IoT gateways. So an IoT gateway has specific functions. It acts as a communications nexus between two networks, typically a private network or the internet itself, and a local network of devices or nodes acting as sensors or actuators. It provides intelligence and storage at the edge of the network, as we mentioned, It aggregates and filters data from those sensors and forwarding only the important stuff up to the cloud when it needs to. And it controls actuators on behalf of cloud commands and ultimately, if it needs to, in response to local events that are occurring in those sensors and devices. Lots of benefits from IoT gateways. A major one is that you can connect legacy devices to the Internet of Things with proprietary protocols and interfaces and potentially insecure protocols and interfaces. And you can assure the communications that are being done with the cloud are secured and safe and protected. And it provides a layer of separation, essentially a firewall, to protect those low-level devices from access from the outside. Gateways can be easily updated and configured and reconfigured via software updates over the air and take on new functions and capabilities, maybe connecting new end devices and new protocols. They relieve the processing overhead requirements of those low-level nodes, keeping them simpler and safer and cheaper and lower cost, and allows you to scale up the overall system by concentrating the intelligence in the gateway, taking advantage of that over multiple end devices. Also, it can help diagnose and troubleshoot device failures of those end nodes, and if they start chatting or getting in trouble, they are isolated and can be separated from the overall network. And it offers local autonomy and intelligence at the edge of the network, and specifically in response to anything that's like a lost connection to the network. It can operate autonomously and take advantage of what it knows to control those actuators and sensors. And it can respond quickly to time-critical events. Gateways come in all kinds of forms. I'll just give you one example. For Christmas, my kids gave me a device that you could call a Fitbit for your car. It plugs into the OBD port on your vehicle, and it monitors engine status and speed and braking and gas mileage and all kinds of other critical data. It forwards that via Bluetooth to your smartphone, and the smartphone app collects it, adds GPS coordinates to it, and aggregates the data, and when it needs to, it updates that information to the internet, to your account up there. And so this device is teaching me to be a more efficient driver. If I accelerate too quickly or brake too hard, it chimes and chastises me for being a bad driver. I didn't think I was ever a bad driver, but maybe my kids thought I was. And so this device is getting more efficient use of my car, and I'm actually seeing increased gas mileage. If there's an engine check code that appears, the device will decode that and present it to me on my smartphone. It'll show me mechanics nearby if I need to find one. And if the airbags deploy, it will send a text message to a set of emergency contacts. It's pretty cool. Maybe that's what they wanted. I don't know. So gateways can exist in many forms. They can exist just as a cell phone app or a smartphone app. When you're building an IoT gateway, developers have a lot of trade-offs to make. They can go with a very customized, build from scratch application written in C or C++ on top of Linux and hardware, for example. Or they can use a high-level language like Java Standard Edition and write their code in Java and gain the benefits and improvements in development time that results. Or they can even go farther down that path and bring in frameworks and services that exist already and layer them on top of Java, and that leaves them to just write their application-specific code as a component of that system. And we'll talk a little more about what that is. OSGi is referenced here. This is a framework for running on top of Java virtual machines. So what does Java bring to the table? Well, first of all, it's a high-level language. It has automatic garbage collection. You don't have to worry about dereferencing bad pointers or stepping on memory when you're writing your code. It has very robust security and exception handling mechanisms. It has a language-defined threading model, so you don't have to depend on a POSIX thread API or all of the issues that come along with that. It has very clean wait and notify and synchronization mechanisms, so threads can cooperate with each other without stepping on each other. It has a very powerful dynamic class loading architecture, lets you load classes and code on the fly and unload it and reload new code as you wish. It's very platform independent. Java really is the most portable language on the planet. It, for the most part, lives up to write once, run anywhere, the promise that was given originally of that product. And it has excellent support for all of the cool things you need to do in IoT, for networking and concurrency and database access, and thousands of third-party libraries that are available, most of it open source, that you can take advantage of and save work when you're building your application. The Open Systems Gateway Initiative is a framework for developing and deploying software components written in Java. Components are called bundles. They hide their internal implementations and they communicate with each other through well-defined services. Bundles can register their services and look for other services and listen for them coming online in a local registry managed by the framework. And they can adapt their functions according to the services they find available. Dependencies and versioning among bundles from different vendors and sources and versionings are all managed automatically by the OSGi framework. And bundles can be, using this same Java class loading architecture, can be installed and started and stopped and then uninstalled and reinstalled, all without bringing down the VM or the system in general. So you can do over-the-air updates on the fly using OSGi framework. Very, very helpful, very useful in the IoT space. There's a number of resources out there to learn more about OSGi in the IoT. More generally, the Apache Felix project has been around for quite some time. It's a full-featured OSGi framework, often used in enterprise and server implementations. It has lots of tutorials and examples and pre-built bundles that you can install and run on your favorite target platform. The ldquo project is an IoT-focused OSGi framework and a set of bundles. In fact, Ian Scarrett from the Eclipse Foundation just spoke an hour before me, and he, I'm sure, talked about this project. It was contributed to Eclipse about 3 years ago by Eurotech, a big gateway manufacturer that uses Java in their gateways. It included services for GPIO and messaging protocols, networking, etc. It runs on the Eclipse Equinox OSGi framework, yet another OSGi framework out there. Equinox is famous for being the heart and soul of the Eclipse IDE. If you didn't know it, Eclipse IDE is an OSGi-based product. And all the modules that run on all the plugins and stuff that run on Eclipse are OSGi modules and OSGi bundles. There's also the Eclipse Concierge OSGi framework, which is very nice. It's a small footprint framework that runs all the usual bundles from both Cura and Apache. It takes about 300 kilobytes of jar file and runs very clean and fast. And you'll be seeing it in the demo in a minute. If you are interested in a commercial OSGi implementation with commercial support, Procist, recently acquired by Bosch, has their MBS product, and it's very targeted toward IoT vendor or users. And the OSGi homepage, of course, is out there. So Open Systems Gateway Initiative was created in 1999, so it's like 17 years old now, by an alliance of companies that were interested in building residential gateways written in Java. They were kind of early to the table and thinking about IoT. And they decided they needed a common spec to build these gateways on top of. And that spec has been improved and added upon. They're up to revision 5 now, I think. And so that OSGi homepage is still actively involved in, and they have reference implementations. Actually, the standard reference implementation is the Eclipse Equinox framework. A lot of compatibility among those OSGi products. All right, now I want to take a moment and step back and talk about an issue that doesn't get a lot of attention when we talk about IoT and gateways in general, and that is the issue of real-time. So real-time response and real-time systems mean that a system must process input or some other information and guarantee a response to that input within a constrained time period, a deadline. And if it misses the deadline, it's considered a failure, even if the response itself was correct. In the case of a safety critical system, you may actually lose a life or a limb if those deadlines aren't met. So real time is best explained, I think, in terms of an elevator bank. If you go to the elevator and you push the call button, consider your expectations about when the elevator was going to arrive. Will it get there in a minute? 5 minutes? How long do you wait before you give up and you take the stairs? Now compare that to your expectations when you press the brake pedal on your car. So will the car immediately begin to slow down? Are you willing to be as patient as you are for an elevator? And the answer, of course, is no. Real-time systems like brake pedals have to be predictable and deterministic and respond in worst-case situations and always respond in that way. So real-time is as much or more about predictability as it is about speed. So when is real-time required? Well, it's required when milliseconds matter to your application. If you press on that brake pedal 9 times and it activates in 10 milliseconds or less, each of those 9 times, and then on the 10th try it takes 2 seconds, well, the average is only 209 milliseconds. That's pretty good. Is that acceptable? Well, no, it's not. So you do have to meet those deadlines under worst-case conditions, under every situation. Real-world, real-time examples here in factory automation. Imagine you've got a tool on a factory floor. It exhibits an unusually high power consumption. Your control system says, I got to take this offline and figure out what's going on. So you shut it down and you reroute your workflow to avoid lost production. You got to do that quickly. In logistics, an automated baggage handling and sorting system at an airport needs to read tags on each bag as they run by a reader and direct that bag to the appropriate gate for loading onto an aircraft. Driver assistance system is looking at a driver with a camera and detecting micro motions of the steering wheel to determine if the driver is fatigued and needs to alert the driver or even make a lane correction or engage braking to avoid a collision or a problem. Energy production, so a wind turbine experiences a spike in gearbox oil temperature, needs to feather the turbine blades quickly and engage a brake before a catastrophic failure occurs. Building automation, HVAC system detects smoke in a particular zone of a building, needs to activate the fire dampers in that zone and shut down airflow so that it doesn't circulate smoke or feed air to the fire. And a public access system, you've got a stadium with entrance gates, and you need to read a ticket and activate a turnstile so that the patron can walk through it in time. So all of these situations are cases where a delay of just tens or hundreds of milliseconds can make a huge difference in outcomes. And that's where real time is necessary. You may or may not know this, but traditional Java virtual machines have trouble with real time. And here are some reasons. They have garbage collector pauses that occur unpredictably at times when they need to do what they call stop the world collections, which means all the Java threads have to stop running while the garbage collector does its thing, finding dead objects and relocating them in memory. That can be problematic to real-time systems. They're just-in-time compilers in most traditional JVMs will jump in and they're turning bytecode into native code for optimized execution, but when that occurs is somewhat unpredictable and may happen at a very bad moment, like the 10th time you push on the brake pedal. So you need to be able to deal with that. Lots of traditional JVMs run on operating systems that use page faults to bring in code and data and stack frames into memory, and so those page faults can cause unpredictable delays and extend the execution time of a critical piece of code. Traditional Java lacks precise timing APIs. You may not know this, but a Java util timer, for example, that's pending for a future wake up is subject to disturbance when you change the system clock in the operating system below it. So if your NTP daemon wakes up and wants to reset the time a few seconds one way or the other at midnight, guess what? Your timer's going to wake up and do something strange at the wrong time, or maybe run more than once than you'd expect it to. There's limited thread scheduling control from traditional JVMs. They mostly just hand off the threads to the operating system underneath, and the thread priority that you may set is really just a hint to the Linux OS or whatever OS is underneath it. And it may, in fact, run low priority threads in favor over high priority threads, so you don't get much control over that. And the worst case scenario of that is when you get into a priority inversion situation where an unbounded amount of time is spent in a low priority thread and it's preventing a high priority thread from running. These are all issues that prevent traditional Java from running real-time applications. So what do you do? Well, you can go, yeah?
How severe is page fault delays compared to others? Can you quantify it?
It can be, well, there's kind of short faults and long faults, right? So if you're swapping in from disk, then it can be a long fault. For example, just bringing a page of code into memory can be problematic. It can take many, many milliseconds, maybe tens of milliseconds to bring it in off a disk. If it's just zeroing out a new page of stack as you're growing the stack, that's maybe 1 or 2 milliseconds and you're good to go. Perhaps, but maybe your application needs sub-millisecond requirements. So you really do have to be careful about page faults in any case. But I'll talk about how you can avoid that. You can go to C or C++, but you lose all the benefits of Java that I just talked about. You can split the application into a real-time part in C and a non-real-time part in Java. Problem with that is not every application is so easily partitioned, and especially if you're trying to embed intelligence in these devices, how much intelligence do you have to write in C and not in the Java piece? And now you've lost all the benefits of using Java. And these things have to usually communicate with each other, so if the real-time part has to ask the non-real-time part for some data or a decision to be made, how long can it wait? You don't know. You can try running the garbage collector in tuned modes. My last count, the Oracle JVM has 4 garbage collectors available within it. I don't know if you knew that, but you can select it on the command line, which GC you're going to pick. And there are entire tracks at the Java 1 conference dedicated to tuning the GC. And it drives me nuts when I see these folks trying to do what they can to make it work. Some developers will just allocate a massive heap and hope that it doesn't fill up before their critical code gets to run. It's not a winning strategy for real-time solutions. There are some pauseless GCs out there. 1 or 2 vendors that are specialized in JVMs focused on the financial market, particularly stock trading. You can imagine that if you miss a trade in a computerized trading environment by a few microseconds, you may lose lots of money. And so they have focused on the GC as a critical issue in enterprise class financial trading applications. And that's fine, but they don't address all of the issues with real time, like priority inversions and scheduling issues and timers. So you can't necessarily count on those to do everything you need it to do. There is also a spec out there called RTSJ, real-time specification for Java. It was JSR 001, I believe. It was the very first JSR accepted by Sun Microsystems. The RTSJ was an attempt to define an API standard under Java that would give you real-time response. Unfortunately, it got very complex, very big to cover all the possible cases and situations that it could be used in, and it requires that you use special no-heap real-time threads to run your application code that's real-time, and you've just partitioned your real-time piece off again, and you can't use all the cool stuff, all the libraries that you'd like to use in Java, not available to you. You got to write them from scratch in the RTSJ side of the world, where they have immortal memory and scoped memory so that the garbage collector doesn't get affected or doesn't affect that code. RTSJ has been dying slowly. I believe at this point there's only 1 implementation out there that you can buy, and it's fading fast. Oracle discontinued its product a couple of years ago. Or you can go look for a real-time Java Standard Edition JVM. And such a JVM does exist. They do exist. And here are the features you need to look for in a real-time Java. Garbage collector needs to be preemptible by any higher priority Java thread at any time. and then be able to resume collecting where it left off. And that means it's a preemptible and incremental garbage collector. Those are the key features of your GC. And by doing that, you are able to run your high priority real-time threads at the appropriate times and not get delayed. You need ahead of time compilation and control over just-in-time compilers so that you can know that it's not going to be interfered with. Your execution will not be delayed by JIT compilation, and you can do AOT compilation, which has its own benefits. And in fact, in JDK 9 or 10 maybe, Oracle is talking about adding ahead of time compilation to their product. You need to be able to lock pages into RAM using appropriate APIs like mlock_all so that page faults don't delay your execution. You need to have jitter-free timing APIs specialized just for your critical tasks that aren't going to get disturbed by changes to the system clock. And jitter-free in the sense that they use absolute time targets for waits and sleeps so that you don't have this potential of a jitter specifying a relative time to when you wake up. Garbage collector and Java threads need to be prioritized and strictly scheduled by the JVM. And the JVM needs to provide control to the user over the scheduler timing and the scheduler, well, just the controls of the scheduler itself, particularly the policy and the priorities assigned over the operating system itself, such as Linux, steadily, and sched_FIFO scheduling policies. Those are important. And it needs to implement something like priority inheritance protocol to avoid the problems of inversions. So real-time Java is only as good as the operating system on top of which it's running. You need to deal with real-time Linux and getting Linux itself to respond reasonably fast. You can get a commercial real-time Linux distribution. There are a number of companies that do this. TimeSys, Wind River, who's here at the show, folks at Red Hat, and also a company called Concurrent Computer they all have real-time Linux distributions. Or if you want to do it yourself, you can apply the preempt_RT patches that are freely available to your kernel and configure it appropriately and build it and get very good real-time response out of that. Or if you don't really need tight real-time response, maybe a millisecond or a millisecond and a half, you can just turn on config preempt and config high-res timers and get your own kernel to respond pretty nicely when you're running in the steadily and sched_FIFO policies, generally under 2 milliseconds or less. Once you have your kernel selected, you've got to deal with some other tips and tricks here. One of them is, since 2.6.23, I believe, the completely fair scheduler showed up. CFS is a great thing. It's a nice scheduler compared to the O of 1 scheduler that preceded it. Unfortunately, it has a default bandwidth enforcement mechanism. So if you have a real-time thread that takes more than 95% of your CPU time in the last 1 second, it's going to suspend that thread for 5% of the CPU time, or 50 milliseconds by default, when it decides you've used too much, because it wants to make sure that somebody else gets a shot at it. So you may not want that to happen. It depends on how heavily you're running your real-time threads. But you can turn that off with a simple edit of the sysctl.conf file in your etc directory, and you're good to go. You need to boost the ksoft_irqd threads. These are kernel threads that are used for distributing signals for timers and things down to user mode threads. Normally, ksoft_irqds are running at a high priority within the sched_other policy, which means high priority threads up in the steadily and FIFO will actually preempt them. And you can get into an inversion situation where you're expecting a timer to be delivered, a timer signal to be delivered to your application, and it can't make it to the ksoft_irqd because it's being preempted by something higher. So you need to boost it to sched_FIFO, usually at priority 99, which is the top of that scheduling range. Very useful and helps deliver timer signals on schedule, which is very important to most real-time apps. You need to be able to use steadily and sched_FIFO policies. You need to call mlock_all early in your process so that you guarantee that page faults are locked in RAM. And you don't get page faults. Essentially, all memory is allocated in physical memory. And then you pre-allocate your heap memory and make sure you stay within that so you don't have to worry about malloc and free or mmap and free presenting a delay in your application. So all of those things can get you to real-time Linux sub 1 millisecond response times. And some of these commercial RT distributions, we've seen response time running our perk Java below 200 microseconds. So it's quite good. Okay, we're going to try to demonstrate real-time Java running on an IoT gateway here. The problem statement I selected is you're an astronaut stranded on Mars. I don't know where I came up with this idea. It just sort of popped in my head. You need to grow enough food to survive until your rescue mission arrives. And so you build a greenhouse inside your habitat, and you're going to grow potatoes. Don't know why I picked that one either. But anyway, IoT gateway is there to automate your greenhouse while you're sleeping or not around. Here are the requirements for your Mars greenhouse IoT gateway. You need to monitor and display the sensor data for sunlight, internal temperature, and pressure. Store that data and transmit it to the cloud at mission control on a regular basis. Now, the round trip communication delayed from Mars to the Earth is what? Did you see the movie? Something like 20 some odd minutes. It depends on the distance, obviously, it changes. So anywhere from 12 to 26 minutes one way. So you need to have local control of lights and heat for your greenhouse so that if a dust storm comes over, you don't lose your crop while you're waiting for a response from the cloud to tell you that you should turn on the heat. And as a bonus, you can track your harvested potatoes and estimate your astronaut TTS. That's an important thing to know, is time to starvation. For hardware, we've got a BeagleBone Black running 1 gigahertz ARM processor. This is this device right down here. Half a gig of RAM, 4 gig of flash, a bunch of interfaces on it. A cadmium sulfide photoresistor is used for sunlight detection, and a integrated I2C temperature pressure sensor is used for the other items, and some LEDs and relays to display and control stuff. The software stack, as I mentioned, is BeagleBone with Debian Linux, which is preloaded on the BeagleBone very nicely. Running PTC Perk real-time Java on top of that with the Eclipse Concierge OSGi framework on that. That's that low footprint 300 kilobyte jar file. And about 7, I guess, services or bundles, if you will, on top of that. All of those, all but one of them are stock Apache Felix bundles that I just downloaded off the web. And the one greenhouse control bundle is the one I wrote. It has a total of 4 Java classes in it, 2 of which are just boilerplate for activating the bundle and registering a servlet. And the other 2, I'll just show you important parts of it here. So this is the BBB Java. This is the low-level interfaces to the sensors on the BeagleBone Black. The run method here just essentially establishes some thresholds for lights and heat. And then it drops in, it initializes the native interface to it. It's got some JNI code that's going to go fetch the A to D converter and talk to the I2C interface when it needs to. And then in a while loop now, every 100 milliseconds, it's going to sample the lights and the temperature and the pressure, store them locally so that the servlet can obtain them, and then it sleeps for 100 milliseconds and comes back around again to do the same. On these systems, on this particular kernel, with the tips and tricks that I told you about, I can get about 1.4 milliseconds max delay. So the worst case, this thing sleeps 101.4 milliseconds at the end of each loop. Here's the Mars.java class. This is the code that implements the servlet. It's got 2 methods, do get, do post. These are in response to browser interfaces, browser requests that come in. Basically, all it's doing is sampling the light and temperature and pressure values, turning those into strings, and then embedding those into a predefined HTML, CSS string that's going to be fed back to the browser, populated with the appropriate data for that current set of values. The do post method down at the bottom just calls do get, and at the top of do get, you notice that it checks for a button that's been pressed called reset. That resets the simulation that's going on of the harvested potatoes, which runs at, I think, 4 Mars solar days per second. So we can watch the the potatoes grow faster than in real time. So let's take a look at the demo. See if I can get this thing working. I had some wiring troubles earlier today, and I'm hoping that it's still okay. The I2C bus pins had come unsoldered. It looks like it's all right here. And we'll fire up now. So we've registered on the servlet server, and we'll go to the Mars greenhouse. There we go. So we've got sunlight detection with a bar graph. We're at 70% of full sunlight. Temperature is at 24.9 degrees C. Pressure is 101 kilopascals. Lights are off, heat's off, and we've got our simulation of harvested potatoes at the bottom. I can put my finger over the top of the photosensor, and now the lights turn on. And I don't dare touch the temperature sensor because it's going to knock the wire loose and I'll be in trouble. But I used to have a can of compressed air that I would blow on it and cool it off. You can't put a compressed air can in your luggage and take it on an airplane. That's against the rules. They will mess with you, so don't do that. The simulation at the bottom, as I mentioned, runs 4 days per second, essentially. So we've elapsed already 263 days, and we've got a 150-day astronaut time to starvation. The number of plants has reached its peak of a 320. There have been 4 harvests thus far. It takes about 75 days to get through a harvest cycle. And we reseeded some of those potatoes so that we can keep growing. So our astronaut's going to live. He's going to make it as long as he keeps up with the appropriate settings here. And of course, if the pressure sensor was wired to a system that would shut down or seal up the habitat, you wouldn't have the problem that you saw on the movie, right? So we could solve Matt Damon's problem here if he'd used an IoT gateway. And I can reset this simulation at any time back to 0 and watch how things progress as well. So let's get back to the world. Oops. There we go. So in conclusion, gateways are really an important element in building a scalable IoT infrastructure. And we think Java provides a great foundation for building IoT gateways, smart, intelligent devices at the edge, not just gateways themselves. OSGi is a robust software component model that adds to Java and makes it more capable. And when a gateway or any other embedded device needs to respond quickly and predictably to events, a real-time Java standard edition is your best choice. And I'll now open it up for questions. Yes? No, it's strictly the BeagleBone Black with its GPIO pins and has an ADD converter on it, so I'm able to run that strictly off the BeagleBone itself. Yep, and it also has I2C. Yeah, they'll pair up another microcontroller with it, and this is strictly the Cortex-A8 and the SoC support for the GPIO pins. That's why I like this one more than the Raspberry Pi. Raspberry Pi doesn't have A to D inputs, just has GPIO. So you have to do something more to get A to D in it. Yeah?
So there's of course, before their Java SE and their Java ME.
Yes. Yeah.
So do you have any metrics in terms of like how they stack up?
Yeah, they do very well when you don't have real-time requirements. Java ME and Java Standard Edition Embedded are very good, but they have stop the world garbage collection in them, and so and they have problems with real-time. They have problems with priority inversions. I can show you test cases that I run. If you fill up heap memory and keep it going, you have a background thread that's generating garbage all the time, you can get that JVM to pause for literally seconds, depending on the size of the heap. Just a modest heap size of a couple hundred megabytes will take 300 milliseconds to clear. So you'll lose a third of a second on some of your critical events if you're not careful. So Oracle didn't design embedded Java or their Java product to be a real-time product. They just chose not to, and that's okay. We designed ours from the beginning to be a real-time JVM. And so there are trade-offs that you make in the course of doing that. Yes?
Go back to memory allocation and garbage collection. So if garbage collector is preempted, how do we guarantee that we don't run out of memory?
Memory, yeah. So you can overrun memory and fill it up with a high priority thread and get yourself to a point where you can't allocate any new objects because there's no space for them, or there's at least no space big enough for them. And when you do that in our JVM, what you end up doing is relinquishing the remainder of your time slice. Your Java high priority thread will relinquish its time slice to the garbage collector or set of garbage collector threads at the allocating thread's priority. And then the GC will get your time sample, and then you get to try again for your allocation. It'll keep doing that. So you can delay execution of a high priority thread if you just fill up memory and just keep driving it to the end with a high priority. So yes, you need to have some background level of CPU availability to keep the GC on pace with your allocation rates. Exactly. And you have to be careful in those high priority threads not to over allocate. And you have to use clever, less memory intensive APIs, like use string buffers instead of strings. If you're concatenating strings, you should be using string buffers and not just adding strings to each other, because you'll create lots of dead objects when you do that. So there's lots of ways of avoiding those issues. And reuse of buffers and allocated objects. Sure, you can drive any JVM to out-of-memory errors, and it'll throw an exception. And you'll find out about that from your calling code, exactly. Yep, can be done. Yeah?
I think it relates to that question. I believe the garbage collector has some sort of concurrency thing where when it's running the code, basically it runs the Java code and it like has every time you move a reference, it has some sort of garbage collector behavior as well as whether or not that pointer is still on top of it. So when the garbage collector runs again, it's still like it still has some state from the previous one, and anything that's changed since then is further that. So I think you were asking like, well, if the garbage collector gets interrupted, you'll forget everything or so far. Not necessarily. There was a slide saying that the garbage collector can get preempted.
Yes.
Real-time thread. What if this real-time thread actually continues to allocate the memory at the
Right.
same time when the garbage collector is waiting for it to finish?
So the garbage collector it is paused long enough to let the high priority thread do his thing. Hopefully it's not too long a period of time, and it'll pick up where it left off in the garbage collection process. But yes, if you're creating new objects in that high priority real-time thread and don't give GC enough time to keep up with that allocation rate, you're going to run out of memory. Absolutely. Yeah. Sure. Yeah, so memory usage can range quite broadly. So at a very minimum, to get a hello world running on our PERC VM, it'll take about maybe 8 megabytes of runtime memory and maybe a meg of heap memory. But that's just hello world. And so now you talk about how much application code do you have? Are you going to ahead of time compile that, or just in time compile, or interpret it? That can widely modify the heap usage of your application and the amount of memory you use in execution. So anywhere from 8 to 10 megabytes up to hundreds of megabytes. We have customers who run regularly million-line Java programs on PERC, and they'll take hundreds of megs. And a lot of them ahead of time compile all of that code so that it's ready and in place and in a deterministic form even as the execution of the JVM begins, and it stays that way. And they like that because it's very predictable execution. They also like it because it obfuscates the bytecode. They don't see bytecodes. They just see native code. It looks like a compiled C app as far as anybody's concerned. So it's hard to reverse engineer an ahead of time compiled Java virtual machine with its application built in. Yeah. Yeah. Yeah.
In my experience, say top priority already has some high level priority,
Well, it's interesting that you mentioned that because I thought so too until I started working with a couple of systems. So Fedora and Red Hat Enterprise Linux, for example, they run it in sched other at priority, well, it's a nice level of 9 or so, but in any case, it's down in the sched other policy, and you need to boost it up into sched FIFO policy, and usually at priority 99 is ideal. I was surprised that they were running it down there. Oh, I'm sure there are some. And if you work with the preempt RT patches at all, they'll tell you to do that if you've got timers that are important for you to be delivered, timer signals that need to get delivered on time. Absolutely. And of course, there's one ksoft RQD for each core in your system, and so they all need to be boosted. But you can do that with a simple script at boot up time. So I'm told that we're out of time now. Appreciate your attention, and if you have any questions, we can talk after this and come find me. Thank you very much.